All right, Saints, we're doing lesson 9.2, and we're actually doing a lesson where the more you don't show your work, it's kind of the better for you. Let me do a proof for you for the first type of special right triangle. We have two different ones that we're going to take a look at in this lesson. Oh my goodness, this is really driving me nuts with this bad pen. So, I have here is a problem that the ancient Greeks faced. So it's this triangle. They were trying to figure out really across a square, right? So like look at this figure and you kind of think of it as half of a square. And we have what's called an isosceles right triangle. So these two legs of the triangle are both equal. What it means is that since it's an isosceles triangle, if one of these is going to be the angles is going to be taken up by 90. The other two acute angles are both going to be 45 degrees each, right? They're going to be congruent in the same way that their legs are congruent that are opposite them. So we'll call this leg X and this leg X. Now, if this were side value 1, right? The question the ancient Greeks had is we knew we could find the area, we could find the perimeter, but what was the length across the diagonal? So it's this right here. We're kind of curious, what is this hypotenuse equal to? All right, so we can, of course, employ the Pythagorean theorem to find out, but this is going to be consistent as we do this. So x squared plus x squared, right? A squared plus b squared, the two legs squared. Their sum is equal to that hypotenuse, which we don't know, some number squared. Now, we can take a sum of x squared and x squared. X squared plus x squared is equal to 2x squared, which is going to be, again, that third side squared. And then we can solve for it, right? If we're trying to figure out what that side length is by itself, we can undo the square, which means we're going to take a square root of both sides. So we'll take a square root of 2x squared, and we'll also take a square root of that hypotenuse, whatever that number is, like question mark squared. Now, you take a square root of a square, and you have just the value by itself. Over here on the left, the square root of 2x squared, well, we can't take the square root of 2. That's stuck inside the radical. And, of course, we call this portion just the radicand, right? So inside of the radicand is the 2. But x squared has a square root, which is just x. So what we know is that this value is equal to x rad 2. In other words, if this value here were 1, this would be 1 times rad 2 or just rad 2. If this value right here were 5, this value here would be 5. Those two legs would each be 5, and that hypotenuse would be 5 rad 2, right? We would just replace the x with 5, right? So this is what we call an isosceles right triangle, which is also known as the following. It's what's referred to as a 45, 90 triangle. All right. So, let's do some examples. First one. We have our right triangle. And we have legs of 22. Solving for x. And again, gentlemen, if you know how to do these problems, you're actually not going to have any work to show. Okay, this means that you've actually taken notes and paid attention, and you're employing this formula for an isosceles right triangle, which is that to get from the leg to the hypotenuse, we are going to multiply by rad 2. So x in this case is 22 times rad 2, or 22 rad 2. Okay? Let's continue on. I have, again, two legs are the same. I know it because they're both marked by the same value or the same variable. Hypotenuse is 10 rad 2. Now, what is x going to be? Well, to go from the hypotenuse to the leg, you're going to divide by rad 2. In this case, it's going to just be 10 rad 2 divided by rad 2 means it's going to be expressed without that rad 2 written, and it will just be 10, right? Because rad 2 divided by rad 2 is just 1, right? We're going to take 10 rad 2. We're going to divide by rad 2 effectively just to get this guy. Okay? All right. And Yet another one. I have a right triangle with legs of rad 2. Because it's an isosceles right triangle, it means it is also a 45, 45, 90 triangle. Meaning to go from the leg to the hypotenuse, I multiply by rad 2. Rad 2 times rad 2 is just 2, right? Rad 2 times rad 2 is rad 4. Square root of 4 is 2. All right. So, new type of special triangle. I have a lot of examples for us to practice for our assignment later. And the second type of special triangle we're going to learn is a really famous one. And first we're going to start with the following. We're going to start with the isosceles, or excuse me, with the equilateral, which is also an isosceles triangle. It's a type of isosceles triangle, which of course we know has, being equilateral also makes it equiangular. And remember what was special in this triangle is that if I were to take this line right here, which is both the angle bisector, not just both, it is the angle bisector, altitude, and perpendicular bisector. Meaning that right here I have a perpendicular bisector. This angle is bisected to be 30 degrees, right? So I have two identical triangles. And within that, I've bisected this side right here. Now, all the sides, I'm going to give them the value of the same consistent value, which is going to be 2x. You'll see why I've used 2x, and I could give it anything. 4x, I could give it just y. But rather than dividing up that variable term, 2x, leave it as 2x, meaning that this side over here on the left is 2x. And this entire side was 2x, but this segment here is only going to be x, right? It was bisected perpendicularly. So, the question then becomes, what is y? And for this triangle, I can employ the Pythagorean theorem consistently. So y squared plus x squared is equal to 2x squared. Now, what's 2x squared? 2x squared is really going to be 4x squared, right? 2x times 2x. That's, again, we're solving for y because we want to know what this length is right here in this smaller triangle. So I'm going to take away. So y squared is equal to 4x squared minus x squared, which is 3x squared. And again, I'm going to solve for y. So in order to get it by itself, I'm going to take a square root of both sides. Y squared is now just y. That is equal to, stuck inside of the radicand, 3 square root of x squared. X comes out. That is your value. Y is equal to x rad 3. So this is x rad 3 right here. So we now have this relationship. This is what's called a 30, 60, 90 triangle, described by the angle measures within that special right triangle. Consistently for all, because these are all similar, because they will all have the same angle measurements, they'll have these proportions anytime that we work with this triangle, all right? So let's go ahead and take a look at one of these 30, 60, 90s. Goodness. All right. 60-degree angle. That's all we're given. But that's all we need, right? Because we already were given that it's a right triangle. So it's a 30, 60, 90. And we're just given the hypotenuse is 40. We need to find x and y. So this is going to be really straightforward, right? Because go back to what we had. If we're going from the hypotenuse to the short leg in this right triangle, from the hypotenuse to the short leg, we're going to divide the hypotenuse by 2. So 40 divided by 2 is 20. To go from the short leg to the long leg, we're going to multiply, right? Because it was, from here, my short leg was x, my long leg was x rad 3. So I'm just going to multiply my short leg by rad 3 to get my long leg, My short leg is 20. So then my long leg will be 20 rad 3. All right. I'm going to draw a few figures here. I'm going to solve each of these right now, just for a little bit of practice, and talk you through the solution for each of these. Oh goodness, really having problems with this pen. All right. Let's top right. The top right, this is not marked as a right triangle. We'll have to figure that out if it is or not. All right. So top left, it's a 30-degree angle. Given that this is 5 rad 3, this is 20. This is 6. And this is 6. All right, so here we're going to solve for x in every single one of these. X, 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 and x. Here we just have to follow the rules of special right triangles. So, top left, all right? This right here, we have 2 legs. The 5 rad 3 that's given to us. This right here is the long leg, and here's how I can tell. Because this is the 60-degree angle, so it's going to be opposite the long leg, right? The 30-degree angles, being the smallest angle, will be opposite the shortest leg, right? It's the triangle side and angle relationship. So opposite 30 degrees is going to be the short leg. To go from short, right, for long to short, we're going to divide by rad 3, right? Because look at what our relationship was. Here, this guy was 20 rad 3. Here, this guy was just 20. So we divided by rad 3 to go from long to short, right? So let's do that here. 5 rad 3 divided by rad 3 is just going to be 5. To go from, you always have to go through the short leg. I want to make that clear. In order to solve from hypotenuse and long leg, you're always going to have to effectively, quote unquote, travel through and calculate through that short leg. Because we want the hypotenuse here. The way we're going to find it, we'll find that short leg, which is 5. And then here, hypotenuse is just double the short leg. So this is going to be equal to 10. All right. Here, hypotenuse, right? Is this a right triangle? Well, yeah, I marked it before on accident. But the reason why it is because 45 and 45 equals 90. And the third angle, right, would have to be, would give us a sum of 180. So 45 and 45 is 90. 180 minus that other 90, that will give us the 90 that's left over. So to go from leg to hypotenuse, we're just going to multiply by rad 2, and we are done. Another isosceles right triangle. How can I tell? Well, these sides are marked congruent, meaning that each of these sides are 45-degree angles. To go from hypotenuse to short leg, we're going to have to take 6, the hypotenuse, and divide by rad 2. Now, we're not going to leave it with a radical in the denominator. We can't do that by rule, right? We learned that in Algebra 1. So we're going to rationalize our denominator, multiply both top and bottom by 1, right? This is what my 1 looks like. Rad 2 over rad 2 is equal to 1. But 6 rad 2, right? 6 times rad 2. And then rad 2 times itself is going to rationalize that, and I'm just going to get a 2. And then I'm going to go here and simplify to get my x being equal to 3 rad 2. All right. And last but not least, remember what we had to do again. We have to go through the short side, so we have to divide by rad 3. So first of all, I'm going to take 6, and we divide by rad 3. Can't leave it that way, right? So similarly, I have to rationalize my denominator. Multiply by 1, so 6 rad 3, right? 6 times rad 3 in the numerator. Rad 3 over rad 3 is that 1 and multiplying by. Rad 3 times rad 3 is just going to give me a 3, which is going to reduce to 2 rad 3, right? And this is my short leg. To go to short leg to the hypotenuse, you multiply by 2. So 2 rad 3 times 2 is 4 rad 3. And that is my answer. So this is how we solve these, utilizing the properties of special right triangles. It's going to take some practice, but we need to review. Remember what a 45-45-90 is. From leg to hypotenuse, we multiply by rad 2. And what a 30-60-90 is, which is that we go through that short leg, right? From short leg to long leg is times rad 3. From short leg to hypotenuse, it's multiplying by 2. Your assignment is in Canvas. Good luck.